So we are facing some standard problems where we are getting warmer and warmer, especially global south, and cooling demand will go up, and then there is shouting saying uh, countries like India will buy more and more air conditioners, which is the easiest adaptation to warming, right? And with the economic growth, people can afford AC, so it's not a luxury anymore, it's a necessity. But then that has a positive feedback on global warming, which we don't want. And then there are also water stress issues, water limitation, water exploitation, unsustainable water use, and so on. So this nice paper with other reports, the other papers that I'm going to combine with, talks about sustainable cooling with water generation. Dual use devices offer a different path for more sustainable living. So generating water from the atmosphere has been going on and has made tremendous progress as well in terms of just using metal organic frameworks and other approaches, desiccants, etc., to cycle air and grab the water vapor that's in there, which is a good source of water, but then you have to also worry about where the energy will come from. So we are combining multiple ideas to see what is sustainable and how multiple existing technologies can be combined to produce water as well as cool the buildings, people, and so on. Most people have experience with this process where if you look at air conditioners, there is obviously cooling going on, drying and cooling of the air to supply to the user, and then there is condensation happening. So most people have experience with this process, from condensation formed from air conditioners to cold drinks taken from a refrigerator. So you take out a cold drink and keep it outside. Temperatures are warmer, humidity is higher, so there is condensation happening on your glass as well. Although conventional chillers are becoming more efficient, integrating a passive radiative cooling strategy in which the sky is used as a cold sink could not only improve performance but also produce fresh water. This may help with the cooling and potentially also with the water scarcity issues in many regions of the world. So Earth is constantly losing energy to space, which is a good thing, otherwise we'll get warmer and warmer. And this is because there is a nice gradient from Earth's atmosphere to space. And can this gradient be used? Nature abhors gradients and tries to keep smoothing them out. So can we use that basic tendency of the universe to our advantage? The water vapor dewing process has a large barrier owing to its inefficiency. So this is where we need some innovations and technology. An established figure of merit known as the coefficient of performance represents the ratio of useful cooling energy generated to the work provided. So coefficient of performance is cooling energy here generated to the work performed. So it goes between two temperatures E and C. So this is the cooling generated by the energy we used for cooling. In general, the COP of chillers depends on the temperature difference between the hot and cold. So TC is hot and TE is cold. Not very intuitive, but here we are. Air conditioning requires air dehumidification, but water vapor dewing introduces a larger temperature difference, and thus decreases the coefficient of performance. This likely requires a reconceptualization of humidity management. So the air conditioner is basically giving you cool air for which it has to dehumidify the air that it's going to pump in after cooling. So these are processes that are required for adapting to warming, and there is the whole issue of making more efficient air conditioners, but here we are talking about exploiting this process to maybe do a dual use sustainable cooling. So dual I'm fumbled that one. Dual use device for cooling and water generation in arid places, which is the most challenging in terms of producing water from the atmosphere. So we'll look at several other concepts. If I don't finish this in one podcast, I'll have a follow-up podcast as well. Hygroscopic, so those that absorb water. Hygroscopic sorbent material captures water vapor from the outdoor air while also lowering air temperature with a heat pump or radiative cooler. Upon saturation, sorbent materials are regenerated by using solar thermal energy or a heat pump. So there is that cycle of absorbing water out, and then you have to remove the water to regain the sorbent material for recycling the process of cooling and removing water. Released high temperature water vapor is dewed. Humid indoor exhaust air and vapor in ambient air are also water sources. Where the latter, the vapor in ambient air, is dewed during the night time by using radiative roof coating. So we are talking about multiple technologies. There are these materials now which are used as radiative roof coating, which can reduce energy use by cooling the buildings naturally by reflecting sunlight. And building cooling and heating are some of the major energy emissions as well. The continuous operation of the dual-use device relies on solar thermal storage. Radiative sky cooling materials provide a cooling effect continuously owing to the atmospheric window 8 to 13 micrometer during the day. So you have outgoing long wave energy, we have visible below that, which is solar energy, and everything is getting heated and emitting thermal energy at these wavelengths. And just schematically here we are looking at water capture absorption process. So we have water release desorption process at the top. So cooling energy is required, and radiative cooling is indicated here, potentially with solar energy, but whatever the approach typically is used these days, obviously energy from fossil fuels in many cases. So you have absorption heat here. So sorbent desiccant is going to do the work for you in terms of water capture, and there is desorption heat, so you have to recapture that heat. So you have water release and desorption, where again you are using solar energy to do the desorption, and you are condensing that heat that is released there. So here are the processes. Dew collecting pipe, one dual use device is here. Exhaust air pipe is here, so this is your cooler. Cooled air dehumidified air pipe coming out here, 4, and freshwater pipe, which is gathering the water that's harvested in this process. Radiative cooling panel, and of course solar energy panel, 7 here. So dew generation happens here, which is part of this system, but it's operating at night to use the natural cooling process that happens when sun is gone down. Okay, very brief, but gives you a sense of what we are talking about in terms of dual use, with the known cycle we use for cooling air conditioners, etc., where we are essentially not bothering to recapture the condensation that happens, right? So how can we improve this process in terms of efficiencies in these various ways of releasing the water that's been absorbed in the first place to recapture the sorbent material? Efficient solar driven water harvesting from arid air with metal organic frameworks modified by hygroscopic salt. So again, we are talking about using hygroscopic salt to capture humidity from the air, but then to make the salt reusable again and again through multiple cycles for efficiency, cost effectiveness, and so on. You need to have ways to desorb or remove the water and somehow do the energy balance there. The abstract: freshwater scarcity is a global challenge threatening human survival, especially for people living in arid regions. Sorption-based atmospheric water vapor water harvesting (AWH) is an appealing way to solve this problem. However, state-of-the-art AWH technologies have poor water harvesting performance in arid climates owing to the low water absorption capacity of the common sorbent under low humidity conditions. So the sorbent ability itself depends on the background humidity, and obviously arid regions have very low humidity. We report a high performance composite sorbent for efficient water harvesting from arid air by confining hygroscopic salt in a metal organic framework, which I have discussed elsewhere, and you can find a lot of material on that as well. The composite sorbent shows 0.77 grams per gram water sorption capacity at 1.2 kilopascal water vapor pressure, so that's about 30% relative humidity at 30 degrees C, which is a good temperature for most of the hot arid regions. And this is done by integrating the multi-step sorption process of salt chemisorption, deliquescence, and solution absorption. Deliquescence is where the hygroscopic salt, let's say, keeps absorbing water and then dissolved and produces a liquid, right? A highly efficient AWH prototype is demonstrated with this metal organic framework that can enable the harvesting of 0.45 to 0.7 kilogram water per kilogram of material under laboratory and outdoor ambient conditions, powered by natural sunlight without optical concentration and additional energy input. So just using solar energy or natural sunlight without having to do PVs or concentrated solar power, giving you more efficient way of powering this system. Okay, so here it is in step 1, which is here. You are doing chemisorption into this metal organic framework. Then you have deliquescence and absorption of water by the salt, and then you have to evaporate and crystallize it and release the so you can see that this is happening at night and this is happening during the day. So we are using natural background temperature gradients to do. So when temperatures cool at night, relative humidity goes up because you know cooler temperatures use Clausius-Clapeyron exponential dependence on temperature and all those good things. And then you have to recover the metal organic framework and do chemical desorption to bring the MOF back to function as for the chemisorption. Okay, very quick, but you can follow up. So this is how you would add to the first idea of creating dual use systems, where you are creating cool air for the cooling of your system, buildings, whatever, and you are using the resulting humidity increase to do water harvesting using these technologies that are done just for water harvesting. Temperature adaptive radiative coating for all season household thermal regulation. So this is another way that cooling is done without focusing so much on water harvesting. So this can be combined with water harvesting as well. The sky is a natural heat sink that has been extensively used for passive radiative cooling of households. So you just use the temperature difference to lose heat. A lot of focus has been on a lot of focus has been on maximizing the radiative cooling power of roof coating in the hot daytime using static cooling optimized material properties, so you can make them light wavelength sensitive. However, the resultant overcooling in cold night or wintertime exacerbates the heating cost, especially in climates where heating dominates energy consumption. Turns out that overall heating energy is much larger than the cooling energy, so there are articles saying we need to stop screaming about air conditioners and cooling for the future and worry about reducing energy used for heating. We approached the thermal regulation from an all-season perspective by developing a mechanically flexible coating that adapts its thermal emittance to different ambient temperatures. So if it's colder, the material changes its properties and then you are not reflecting as much energy. Fabricated temperature adaptive radiative cooling TARC optimally absorbs the solar energy and automatically switches to thermal emittance from 0.20 for ambient temperatures lower than 15 degrees C to 0.90 for temperatures above 30 degrees C, driven by photonically amplified metal insulator transition. Amazing, right? Simulations show that this system outperforms existing roof coatings for energy saving in most climates, especially those with substantial seasonal variations. So we can combine this to do rainwater harvesting and the cycle. So here is how it works. Sky window emittance efficiency EW going from 0 to 1. So you have metals and radiative coolers, and you have the house to be kept warm during cold conditions or at night, and you want natural cooling using the sky temperature during the day. So if the material can reduce the heat loss during the night and do much more heat loss during the day, then you get your complete day function happening. Very nice idea. Moving further, global potential for harvesting drinking water from air using solar energy. So these kind of ideas focus more on water harvesting, but worry about how to manage the energy demand for doing this. Access to safely managed drinking water remains a global challenge and affects 2.2 billion people. Solar-driven atmospheric water harvesting, AWH, that we discussed before, with continuous cycling may accelerate progress by enabling decentralized extraction of water from air. So you don't need to be on the grid. You are somewhere sitting, let's say in the middle of the desert or semi-arid region and so on, doing your water harvesting. But low specific yields and low daytime relative humidity have raised questions about their performance in liters of water output per day. However, to our knowledge, no analysis has mapped the global potential of AWH despite favorable conditions in tropical regions where 2/3 of the people without safe drinking water, safely managed drinking water live. So this paper is much more about figuring out the water harvesting potential across the globe, and the paper provides maps that I want to show here. Here we show that AWH could provide SMDW for 1 billion people. Our assessment using Google Earth Engine introduces a hypothetical 1 meter square device with specific yields profile of 0.2 to 2.5 liters per kilowatt hour at 30 to 90% relative humidity respectively. So I won't read this further. So they're not relying on any specific technology, but they are just using humidity and temperature variation data across the globe to show that if you had a water harvesting system in this range of efficiency of specific yields of water per kilowatt hour, then you can make plenty of water in the global south where people without with serious water problems live. And they have examples of suitability of household scale applications of the atmospheric water harvesting systems. And these are decentralized units, just like solar panels on rooftop. You can have a AWH somewhere on the rooftop or elsewhere as well. So the device types here, passive and active. So these are passive and active here. Dew harvesters, sorption based energy requirements, size requirements, global assessment, where is the niche potential, where is the wide climate applicability. So if you have energy to spend, then you can do it in more places than if you're relying on passive devices. Continuous or multiple cycles per day device types, fog harvesters, sorption based cooler condensers. So this is getting towards the idea of having dual use systems. So I won't read again, but you know the idea that there is potential to harvest water from the atmosphere based on this analysis, given a system that can actually extract water. Terrestrial radiative cooling using cold universe as a renewable and sustainable energy source. Again, if there is always a gradient from Earth to the outer space, this gradient is an energy gradient, and can we use it in some way? Photonic materials designed at wavelength scales have enabled a range of emerging energy technologies, from solid state lighting to efficient photovoltaics, that have transformed global energy landscapes. Daytime passive radiative cooling materials shed heat from the ground to the cold universe by taking advantage of the terrestrial thermal radiation that is as large as the renewable solar energy. Outgoing energy is as much as the energy we can harvest. Newly developed photonic materials permit sub-ambient cooling under direct sunshine, and their applications are expanding rapidly enabled by scalable manufacturing. We review here the recent advancements of daytime subambient radiative cooling materials which allow energy efficient cooling and are paving the way toward technologies that harvest the coldness from the universe as a new renewable energy source. So again, this is about cooling technology, not worrying so much about water harvesting, but we already know that we can combine these. Next, exploiting radiative cooling for uninterrupted 24-hour water harvesting from the atmosphere. So the first paper we looked at is talking about combining all these and creating a system, dual-use system that cools and harvests water. So we are looking at both. Atmospheric water vapor is ubiquitous and represents a promising alternative to address global clean water scarcity. Sustainably harvesting this resource requires energy neutrality, continuous production, and facility of use. However, fully passive and uninterrupted 24-hour atmospheric water harvesting remains a challenge. Here we demonstrate a rationally designed system that synergistically combines radiative shielding and cooling, dissipating the latent heat of condensation radiatively to outer space with a fully passive superhydrophobic condensate harvester working with a coalescence-induced water removal mechanism. So this is essentially what is a dual use system, but here they are much more focusing on energy for water harvesting. A rationally designed shield accounting for the atmospheric radiative heat facilitates daytime atmospheric water harvesting under solar irradiation at realistic levels of relative humidity, so you can use it in dry regions as well and not just coastal humid regions. The remarkable cooling power enhancement enables dew mass fluxes up to 50 gram per meter squared per hour, close to the ultimate capabilities of such systems. Our results demonstrate that the yield of related technologies can be at least doubled while cooling and collection remains passive, thereby substantially advancing the state of the art. We're getting close. One more. A comfortable high efficiency heat pump with desiccant coated water sorbing heat exchanger. So now it's not about water harvesting, but heat exchanger, which is relevant to the dual use we are interested in. Comfortable, efficient, and affordable heating, ventilation, and air conditioning systems in buildings are highly desirable due to the demands of energy efficiency and environmental friendliness. Traditional vapor compression air conditioners exhibit a lower coefficient of performance that we talked about, typically 2.8 to 3.8, owing to the cooling-based dehumidification methods that handle both sensible and latent loads together. So to dehumidify the air that we want to cool and give it to people needs energy, and coefficient of performance suffers there because it has to remove sensible and latent heat loads together. Temperature and humidity independent control or desiccant system has been proposed to overcome these challenges. However, the coefficient of performance of current desiccant systems is quite small and additional heat sources are usually needed. Here we report on a desiccant enhanced direct expansion heat pump based on a water sorbing heat exchanger with a desiccant coating that exhibits an ultra high COP value of more than 7, so 2.8 to 3.8 to 7, without sacrificing any comfort or compactness. You see, they have thought about all these issues. The pump's efficiency is doubled compared to that of the pumps currently used in conventional room air conditioners, which is a revolutionary HVAC breakthrough. Our proposed water sorbing heat exchanger can indefinitely handle let me read that again. Our proposed water sorbing heat exchanger can independently handle sensible and latent heat loads at the same time. So the temperature difference is sensible and condensation and vaporization is the latent heat, right? We already know that. The desiccants absorb moisture almost isothermally and can be regenerated by condensation heat. This new approach opens up possibility of achieving ultra-high efficiency for a broad range of temperature and humidity control applications. Again, not focused on water harvesting, but the system is open to that. Adsorption based atmospheric water harvesting, I won't read too much, I think that's the end, so let's just wrap it up. Atmospheric water harvesting is a promising solution to the world's water shortage. Meanwhile, adsorption based atmospheric water harvesting has shown a higher ability to supply water in arid areas using clean and cheap energy. We talked about the problems elsewhere of doing this. Numerous modern adsorbents for this application have been introduced so far, and many prototypes have been provided. However, there is still a long way to go for widespread and practical use of this technology. Dedicated designs, operating strategies, environmental compatibility, and energy supply are issues that still need further consideration. This article has tried to summarize what's been achieved so far and analyze the challenges ahead and provide solutions to continue the path. Definitely you want to read this if you're interested in those details. So this is the schematic of adsorption based atmospheric water harvesting working procedure. So here you have dew point temperature, partial pressure. So adsorption happens with an adsorbent agent. So water molecules are taken in, and adsorption heat is released, which has to be captured, and you have to obviously do something with it. So that's where the switching happens, where you need to, again, depending on dew point and partial pressure, adsorbent has to be put through heat to remove water vapor. So desorption process is needed, and then the water vapor that's extracted here has to be condensed. So there are obviously energies needed for driving flow and driving adsorption and switching to desorption and doing something with the heat that is released, which is what the dual use is all about. So here you are adding heat and taking the water vapor out and condensing it and releasing it. So this I should have probably put in the beginning. This is where all these different approaches have to be used in terms of creating a cooling system where you also can then use the condensed water for purposes of water use, so that you're combining cooling and water harvesting together. That's a long podcast, but at least I squeezed it into one. Longer than I usually would like to do, but nonetheless I will leave it as it is. Okay,